Well, let's go. We have an hour. It will be a journey. Today we will talk about the new garbage collector from Go since the 125 experimental, and now it's the default. So, who's talking? Now I have time to relax and talk. So, I am this figure in the whole internet. I usually don't use my own photo. The history of this is I work remotely. People always thought, oh, let's play this game of drawing something. And one person thought, I draw you. I thought, okay, so it's my avatar now. I'm a principal engineer in a healthcare company in Brazil called Mehmed. And I do a lot of stuff, not necessarily with the right consistency or discipline. So I wrote some books. I do this kind of thing we call speaker, but everyone speaks, so everyone is a speaker. I do technical revisions in general for books from Manny, from Pact, and other publishers. I do mentoring, not all the time because I need the time to do it correctly. And in the era of AI, I still program, so I'm a programmer still. And lately I have an affairs with Zig, but don't spread it too much because golfers are territorial. So, I have 2 books. The main subject is the same, but the level of the complexity will be shown in the books as different. The book in Go is an intermediate level. And Learning Zig is, I don't know, literally nothing. I program at most 6 months. Yes, this is a book for people learning Zig. Not I debug kernels. Your book is not very useful for me. Yeah, it's not for that. So, one thing, I didn't sleep, so I'm slow. So, I like the community a lot. So I do my financial suicide, so I am here. And I'm in a challenge with Taylor Swift, who has the best world tour. I think my world tour is the best because I fly to economic and she's in a private jet. So, enough about me. What's the problem? In 2024, we have a measurement about the garbage collector. 85% of the time is GC doing the marking phase of the mark, sweep, tricolor, concurrent, a gigantic name for the algorithm. But 85% of the GC is marking, but this part is important. 35% of the CPU cycles are waiting for the memory, is memory stalls. So, I don't know if everyone is onboarded in the concurrent, tricolor, mark, and sweep. A little refreshment. Tricolor, white, gray, and black. White is, you are a garbage candidate. Maybe I get you. Gray is, I'm working on it. This is in the work to be collected. And black is, I already scanned it, basically. What can we do? How can we get this garbage collector from Go 123, maybe, faster? The first thing everyone will say, put more cores. Or in case of Kubernetes, more pods. It's solved. Or SIMD. SIMD is trending. Put SIMD is much, much faster. The answer is go faster. Right? It's just go faster. Yeah, not really. If you put SIMD in this problem, the computation is 2 times faster. It is. But 35% of the cycles are stalls. It didn't change. But one important thing changes. 65% is on computing. You have a lot of time doing nothing, just waiting for the memory. 52% of the time waiting. You are faster, but waiting more. It makes sense, right? I do my bunch much faster, so I have much more time to wait, much more. The name of this problem may be that people give names for everything, but I think the most popular name for this is memory wall problem. What's the point of memory wall? We have RAM and all levels of the cache of CPU. So these kind of memories have a linear progression. L1 is 4 cycles, is very, very rapid for CPU to get this. If you compare with to RAM, it's more than 100 cycles, but it's linear. But we have a problem here. The CPU, in general, is gotten exponentially faster. You have better CPUs that maybe no one imagined, but the memory, not that much. Maybe at 10 or 12 years ago, 16 gigs of RAM is normal. So the time waiting for memory is the gap is getting wider. I have a clicker, okay. I know, I'm slow. Okay, so in 2000, I will say all the names not Brazilian wrong. I'm okay with that, okay? So Boehm is the guy in 2000 that make the analysis of garbage collection and said, okay, 33% of the time is stalled, in this case, yeah, waiting for memory. It could be RAM, could be L1, L2, waiting for memory. For the first load of an object in a process of garbage collection. 32% in 2000. 2024, 35%. It's not getting better. It's getting worse with time. 24 years later, we are waiting the same time, sometimes more time. The memory and the CPU basically is getting tens of times faster or more available. Still, 30% of time, 35% of time, waiting for memory. So the answer is go faster. No, because even if you add SIMD or more parallelism, it don't fix the problem, because the problem is not how fast you go. The problem of GC is memory bound. It's not CPU bound. You could put the best CPU in the world. The problem is the memory. What is inside? How can we make the GC faster? It's 2026, right? So, what I imagine, Google team goes to Claude and asks, hey, read this code base and make the GC faster. Don't make mistakes. But I remember, it's Google. They can use Claude. They ask for Gemini. But Gemini is too good for that. Well, maybe AI is not the answer here. But if you try by yourself, make the GC faster, that is an answer. Turn the Go GC, reduce allocations. It's valid. It's not hallucination, it's valid answers. But none of the answers basically point you to Chair and Garner. And now you are thinking, what the fuck is this, guys? Who is Chair and Garner? Bear with me. Let's make a discovery, a genealogy of GCs. Well, remember, if we make the computation faster, 2 times faster, 4, 5, blah, 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 faster, we are stalling. Oh, SIMD, parallelism, don't correct this. It's not a CPU problem. A guy, probably with a name bigger than Cher, but this is the part that I know. Look for the Boehm, the guy from 2000, and make some evaluations on the work and make progress. The idea is, okay, the prefetch on gray, during the tricolor, the gray part, the idea is right, but not the timing. When Cher is saying that, the point is, okay, you're trying to prefetch what the working list, the items that will be collected. But you do that too much fast. You need to wait a little bit. And a little delay will help you to fetch better. So the result of the analysis is, I will read because it's long. Many prefetches arrive too early. The object is evicted from a cache before the stack unwinds to do it. And many arrive too late. What's the problem with that? You are leaving time to... It's over? No, okay. You're leaving no time to prefetch. You go, prefetch. Okay, I will prefetch more. What's in my hand? Nothing. That's the problem with 2000 guy. So, what's the great discovery in 2004? Prefetch without timing is a weight of prefetches. It's kind of obvious because we know the answer, right? But the data... Hello? Okay. The point is, the data structure that will discover the objects in the garbage collector don't need to be the same that decide if I will prefetch or not. So the great idea from the 2004 guy, Cher, I think Cher, is let's separate these two concerns. So the concern is we will insert a queue, in this case first in first out, between the mark, what objects will be collected, and the processing. Now we have a new structure for that, dedicated for that. We'll pop from stack and prefetch the address and start to enqueue. Enqueue in what place? And this new queue, that is first in first out. This queue is what will be collected. So I will return the oldest entry and life is good. We have the cache line that will not be aggressive thrashed. Animations, because it's easier than I saying things. So when I see Cher, Boehm, load, okay, prefetch was empty prefetch. In the case of Cher 2004, note, it will prefetch only in the last one, so it buffers to do to fill up this queue. Okay? It's running in loop. If you didn't notice, so that's it. And a gardener appears in 2007 and said, okay guys, don't check if the child is marked before enqueuing. It's a problem. Enqueuing all children. When? Always, unconditionally. So, it's every decision in engineering case is a trade-off, right? The trade-off is we have 40% more work list items, our queue. but both is marked and pointers hit the same prefetch object, the same animations because it's easier. What you have here, the queue starts to get things in the working list, and the pop happens too fast. A miss, 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 miss. And the garner, it happens with more hits because it's unconditionally. So, if you have more entries, bigger is the gap. It's super effective. So it's the gold standard until now. Green tea. Do you guys know why it's called green tea? Anyone knows?
Because they added green color?
Maybe, but no. The idea of the green tea is Austin Clement from Go Team was in Japan, trip or not, I don't know. Who needs holidays or who needs vacation when you are remote, right? So the idea of green tea is in Japan, drinking green tea when he had the insight on how to make the GC faster. It's just because of that, but I have my own conspiracy theory. I have one. I think it's green tea to poke Java. Just for that, because coffee makes you agitated, and a good green tea don't make you in that way and make you faster in the same way. I think it's that the true version. So everyone have a favorite conspiracy theory, right? What's the main difference from the old era of GCs and now with the green tea? If you look for the true color mark and sweep, you need to look in locations that's not necessarily near in terms of memory. So you could go to the last part of your memory, then in the middle, then the last again, then in the part right on the beginning. And it has a cost. The cost is there is no cache line. Every time you access something, no cache line. You go slow because there is no cache to go, basically. And what Controller makes is a graph and follow the pointers, start to marking, and the elements marked go to this queue. Sometimes it's called the working list, sometimes it's called gray. It depends on the literature. I don't know. Correct. The problem with the current GC, imagine I'm in the past, right? Because green tea is already exists. It's looking for live objects, no matter what they live. The consequences getting more and more obvious. And that's why the backstory. So, what the questions that make everything flips? It's written, I know, but I will say it anyway. What's the next span to sweep? Span is just a bunch of memory, but sequential. You can imagine, but it's not that, an array. There is no array distributed in the memory. Array is a block, a continuous block, right? And I'm working in pages now, and not with objects. The problem of the object is I don't know where the objects live. So they flip the structure, and instead of poking, this memory, this memory, here, now is sequential. It's getting clear, right? It's getting obvious. What the old GC does, find the object, jump to another object, jump to another object, and always receive a cache miss. Always. Always is not true, but yeah, kind of always. The green key is sequential. How sequential? 8 kilobytes, and that's it. 8 kilobytes sequential. So your cache will be probably warm most of the time. Most of the time. And the main difference on this technique for the previous one is you don't need to make the prefetcher via software. All the GCs in the past send, prefetch now, all things like that. Now you can basically trust in the hardware. How it works. This is if you don't get anything until now, if you get that, it's good. So, GC green T. 1. He marks the objects as live. It's live. It's in queue the entire 8 kilobyte span. Oh, but I have just 1 or 2 objects inside that span. Didn't ask. This is I am the green T now. When it dequeues, it scans marked objects, the selected ones, in this span of 8 kilobytes all together. If it's sequential, there's no random jumps. Basically, your cache miss drops 50%. What you should expect if you use a green T. So, if your application is using around 10% NGC, you probably gain 1 to 4% in performance. Oh, my 1% is too little. Okay, but it's free. Why are you complaining? So, if you have a gigantic workload like Uber or because tons of repetitive microservices, 4% is a lot in the AWS bill. It will not change your life, but remember, it's free. You don't need to do nothing to use the green T. Now, I'm coming back to performance later. Let's take a look in the implementation of GC, because I tell a story in drawings, animations, implementation. It's as simple as just one struct to understand how the whole green T works. The name of this struct is span inline mark bits. The last field is called class. I need water. I have 1 hour, right? Okay, you can wait. Boa. Okay, the last one is, what's the size of the object? It could be numerous sizes. It's basically to make the memory alignment in the correct way. You need to know what the size. Hello? Okay. You need to know the size. It's the easy one. So, you have scans. Okay, what scans means? It's not clean code, call Uncle Bob, no. Scans is, you have 540 bits to answer one question. What objects were scanned? That's it. What were scanned? And we have 404 bits to answer another question in terms of marks. Not marks from capital, marking. What objects were marked as live? Were scanned? Were live? Scanned, live. Scanned in? What's the, okay, live in, This is the only two options to be tracked. Cool. But why 63? Anyone has idea why this number, this Kabbalistic number, this Baba Yaga number? 63. Yes. The good point is nobody heard. I will be clever anyway. Why 63? Because 63 plus the 1 byte of owned, the 1 byte of class with more 63, it fits the cache line. It's only because of the cache line. If it was 64, probably we need to use one line more. I'm not the implementer of this, but it's cool, right? It's 63, but let's have a reason. It covers most of the size of cache lines we have in common processors. So we have two things happen at the same time. The marks, we are marking, and the scans. Remember, marks and scans, marks and scans. Not at the same time, concurrently. How green tea knows if it did what they meant to do? They look if the difference between these two exists or not. It will be clear in a second, I think. No, it's not be clear. Let me show. Okay, the point is, you have marking going too fast because of spans is finding it faster than the scans can do, or anything in between. There's no problem because the difference between these two values determine if there is more things to be done or not. It makes sense? There are two values. These two values will be combined in a simple equation called subtraction. That is 0 remaining. Yes, I'm done. That is more than 0 remaining. Maybe I have more work to do. It's as simple as that. The more elegant stuff in software engineering basically are simple things. Okay, but there's one field left. Owned. It remembers me old memes of internet, owned. But the point is, span, scan ownership. Remember, we mark and we scan. Now we are saying, who owns the scan? That's the question. The answer for a group or a span is it's unowned, nobody owns it, one mark, or many mark. We have these three states. If one of these workers try to get and it's unowned, it make a very fast atomic compare and swap. If I can use it, one mark. But at the same time, another worker could be looking for the same object and say, well, okay, I want to track this too. But it's already has this one mark. Now it's, shockingly, many mark. The point is that it's no lock to do that because it's an atomic package, so no contention, no mutex, no nothing. And the answer for why many mark, I could use maybe unowned and owned, and that's it. It's owned or not. Yeah, but with the two states, we are solving just if we are doing duplicate work or not. With three states, we can do more because 3 is better, is greater than 2, okay? But the question is, someone marked while I'm mid-scan. I have a span, I'm doing this scan, but another worker is trying to mark the same thing. I want to know it's happening. Because if you remember, maybe it's an analogy. A memory allocation, you don't want to do double free, right? So imagine many mark like, well, someone is already freeing this. It's better not free. So, span queues. We have a mark, we have a yes. These two operations occur in a span. So you have a span queue. First in, first out. If enters, if more things enter to be scanned or marked, it will be the first thing that will go out. It's literally what FIFO means, but it makes us accumulate more work before it starts doing the job, because it was last in, first out. We have 3 new things. Oh, pop, 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 because I need to be so fast. So FIFO give us the capability of buffering what we need to do with these spans. If we do LIFO, we probably is popping things and fighting for these little resources of span. So, animations. If you look in the LIFO one, in the left, one thing is marked. Very rapidly it's popped because it's LIFO, right? And FIFO, okay, enter 10, give me your burst, no problem. I will push in my own capacity. Do you remember the paper, All You Need Is Attention? It's very famous in the world of AI. This one, all you need is locality. We are talking about cache. So, what we are defending ourselves in terms of green tea is objects before spans. We are avoiding cache misses and inter-span work in general. Local before global. The cache line is bouncing between cores. We don't want to do that. P local, in this case the process. The ring buffer first, the ring buffer of the local. We don't want to chase pointers, even still the pointer is in the runtime. It's still from other P's. If you remember how the M to N and Go works, threads, Go routines, there is a working still happening. It's not the topic, but we can chat after. We want to avoid the lock contentions on the queue, and the global queue that exists in the global queue, right? We don't want to lock this global queue. Everything here is to maximize locality. And locality is important to save cache lines. Cache lines are performance. Data-oriented design is life. What you can expect. Okay, remember, it's free. You don't need to do nothing. You are here just to understand what's happening in the GC. I could be lying in Go Team 2. You just do your benchmarks. So, who is the good candidate to have the best, to get the best quality of this GC? When you have many, many small objects allocated together, hello gRPC, dense spans that are clustered in terms of your locations, and the GC is measurably, I think I will try again. GC is a measurably bottleneck. How do you know that? Measuring, profiling, not saying It seems like slow. I'm slow today, not the GC because vibes. So, we will not receive any improvement if you have a lot of scattered allocations. You have massive objects. Did you guys remember the memory ballast? We don't need to use that anymore, but with the green tea, there's no sense. So, and GC is not the bottleneck. GC is not the bottleneck. You are looking for GC to gain performance. Okay, I know people like SIMD a lot. I need to talk about SIMD. I can go further without SIMD. I know. SIMD is the new fashion, the new kids on the block. Okay. Why SIMD wasn't possible before? It's the first question. Not it's cool, why we use it everywhere. Because the shape of the data in terms of collection is irregular. We had different sizes, allocations happening in scattered places, and the layout of these variables is not very simple to vectorize based on the current layout on the now it's old or legacy GC. So you are using SIMD, you are receiving nothing. With green T, the history with SIMD changes because now we have a predictable data. How predictable? 8 kilobytes. When? Always. When? Always. And after that, again, because it's a computer. So with the green T, we have this packet mark bit. We have this guarantee of uniform layout, sizes. Everything is following a rule now. Shockingly, it's better, right? So it's a few lines. I'm slow. And this is the whole SIMD algorithm inside the green T. We are registering 512-bit registers at the same time. How to do that without SIMD? Allocating a lot or having sufficient space on the stack. And now, Uncle Bob is crying because of the name of this function. Right? Anyways, this is a function with a lot of letters and numbers. Basically, it's saying, do a bitmap expansion using matrix multiplication. And that's it. Why? It's called magic structure because we have magic numbers. Remember Martin Fowler refactoring magic numbers. So we have this thing called Galois. I don't know, maybe it's French. Galois field. It's 8 by 8 bit matrix multiplication. It was introduced to make cryptographic stuff. This is the main motive to this thing exists as an structure for CPUs, processors. That's the reason. That's the reason. And people like to use things for other purposes, right? So it's literally what happens. Oh, okay, it's the same. Yes. We are using this to mark the bit and n bits in the span saying it's marked, it's not marked. Remember, when we are saying about SIMD, we are saying about multiplications in vectors, right? You can do. What is SIMD, by the way? A single instruction. One instruction, multiple data. How multiple? An array. Remember, 63 positions array, 1 instruction, and 6 repositions. Okay, now the difference is if your span is dense, it's dense or sparse. Because if it's dense, in this case, dense is, I have a lot of things in the same span is small objects. So SIMD makes sense because I need to mark multiple data with a single structure. If it's sparse, that's why. And that's the case. You don't need to choose. Remember, it's free. When SIMD will be done, you don't need to choose. It's free. You don't need to choose. I like this. So runtime chooses this for you dynamically. How it decides if this is dense or if it's sparse. There is an equation. You can look up the code, but okay. Continuing. So we have 3 levels of fallback because there is SIMD, but you can use SIMD in every place in Earth because sometimes your processor don't even have this available. So the first try is the architecture. You need this AVX-512 plus Galois words, and when it's available. Since Ice Lake 2019 or in AMD Zen 4 2022 and beyond. So if you have this family of processors, probably Go will use SIMD in dense spans. But if I have my old computer, my Windows XP with Celeron, it will not use it. That's it. Else, no use. So, size class. Remember a field from the 4 fields? Ownership, the 2 arrays, and size. This size here is important because only some classes of sizes have SIMD kernels. And the other, shockingly, don't use SIMD. So, again, the span density is important to enable this threshold and start the SIMD to work. Oh, I have another condition. What do you think will happen? The third option. SIMD or not SIMD? Okay, now performance. The traditional GC is costing 100% of our baseline in this hypothesis. When you start to use a green tea, now you don't have this option you are using, it's free. It's already less CPU being used. But if your host machine has the SIMD capabilities, 10% left. Conservative estimate, because people like to do sketchy performance to say you are wrong, so 20 to 50% total improvement. In any machine in the world? No. Okay. Why Go? Not Java, not any other language with garbage collector could do this. Why Go? Here is a little bit more theoretical. So, we have 3 constraints in Go, and this is the design of the GC that help us to achieve green tea. The first one is the GC of Go is non-moving. So, the content of these spans are always stable. It is not changing places, it's not generational, something like that. So, the main thing here is objects won't relocate while queued. I put it in the queue. Where is the object? In the same place. The second constraint is segregated fits. I'm not talking about this country. So fixed offsets, regular layout. This is what makes it possible. The function that Uncle Bobby hates, and it works because the expansion rate is constant per span. Constant, because nothing is moving. The layout is the same. It's different things, right? It's not moving. But imagine it's moving. It's the same, but not moving. So it's not the same, it's not moving. And non-generational. I don't know, but if I remember correctly, C# is generational GC. So we have the maximum leverage to scan because we don't get snapshots. This is the generation, this is a new generation, this is a new generation. No, it's always in the same place. The object is not moving everywhere. So it's basically cache friendly. If it's cache friendly, it probably be SIMD friendly, green tea friendly. And why I'm putting that constraints? Because they are. It's non-generational. What we cannot do, be generational. Nothing of this was planned. This is the funny part. The non-moving garbage collector is from 9.6. The size class is the last field, and inline spin, no spin is the other. The last field. So the size class is 9.6. Span stable, I don't know the year, I don't put it. So 2024, FIFO scan. SIMD ready. The thing that you use for cryptography, use it for other things. Nobody sits in a round table to discuss green tea. It's a consequence of this independent stuff and progress of the discipline of creating garbage collectors. In our case, our Go green tea, the constraints are not being limit. It's not limitations. They were structural, because if I can change this is my reality now. And this reality is perfect for green tea. That's the point. For me, the funny part is the idea waited 20 years for caches to grow. Because even if Clement or any person before make the same insight, it will not possible because caches are too little. So too small. A lot of words for something. Too small. So 20 years, why it's possible now? Cache is now big enough. You can put the working set. Everything you are working in this process of collection fits. The memory wall got worse. It's a problem, but it put pressure to solve the problem. The concurrent GC, Go has a concurrent GC. Concurrency, tricolor, mark and sweep, gigantic name. Concurrent GC became standard. We're not coming back to a no concurrent GC in Go. So we unlocked this design. The hardware prefetchers got competent, so we don't need to say, oh, prefetch for me. No, okay, just do your stuff. And now we have, heaps exploding. It's not uncommon to see applications in enterprise world using 50 gigs of RAM. What? This exists? This is a small one. So you want to go further in these parts of the theory. I recommend, it's the best book, I don't know, I recommend this book, the Garbage Collection Handbook. I need to buy this book if you want, yes, but gchandbook.org, it's free. You can ask for GPT, but it can hallucinate. I recommend you to read like a human from the 3 years ago, right? So, reality check. Reality check. Oh, green tea is awesome. I'll start to use it tomorrow. It's not a choice. Okay? It's not a choice. You will use tomorrow because that's the default. But reality check. It was an enhancement, not a replacement. Sometimes when you said, no, green tea now can do this all good stuff, but it's coexisting with the concurrent, three-color, mark sweep. It's joined. Now it's more complicated to maintain. It's not my job. Great. So it's dynamic, more clever, eventually faster, and locality is one of the things that the Go team, allegedly, is concerning. So basically, we can summarize everything in, hey, did you know data-oriented design exists? This is the whole talk. So, good benchmarks. 0 production improvement. .hub. .hub has a case. They tried the garbage collector green tea while it's experimental. In this case, nothing on the algorithm changed. It's just experimental because safeness. And this is the headline. We tried the Go experimental green tea garbage collector. It didn't help performance. It's not magic. The case of .hub is B3 nodes, large objects, remember? Few for span, not dense. Create over seconds. 2. The interior nodes in these trees are scattered. No temporal clustering. No span collocation. Now you know why this is maybe silly. But imagine you 1 hour in the past. It's not that simple. I'm not mocking because I think .hub are dumb. I'm joking. It happens. Joke is a thing that exists. So, good benchmarks, 0 production event, because I put the backwards, okay? This is the expectation. Oh, we are gaining at least 20%. At least 20%. Reality, 0. Now, I believe most of you know why it didn't reach the result. But it's not obvious. We walk this journey together. This is the question for the people that always not paying attention. It will help my app. You are saying things. Do you have my app? Yes or no? So it's a fluxogram kind of decision tree. So the first question is, your GC is using more than 5% of CPU? No. Won't matter. Nothing to do. Oh yes, it's more than 5%, okay. It's small objects. No. Won't help. Okay, yes. It's small objects. The allocations in this case are bursty and clustered or everywhere? No, it's minimal. It's like .hub. What you're expecting. The last one is yes. The cache miss radio. is greater than 5% true? No. Is already cache friendly. Nothing to do. If all questions is yes, GoInT should help. What you need to do? Nothing. It's free. It's nothing to do. I'm only saying when you do benchmarks, don't try to catch known problems. Basically. So, benchmarks measure one thing. Production measures everything. Green tea didn't make the GC smarter. It made GC friendlier to caches. In other words, data-oriented design. Thank you.